Welcome everyone to techaily.ai. We're kicking off another deep dive today, and we're really thrilled to have Stonefly as our sponsor for this exploration. Stonefly is your trusted solution provider and advisor in, well, a whole range of areas. Enterprise storage, backup disaster recovery, hyper-converged VMware, Hyper-V, Proxmox clusters, AI servers, SA365, which is a turnkey security appliance, and public and private cloud solutions too. You can find out more at stonefly.com. Definitely check them out. Okay, so today, we are tackling a technology that is, it's absolutely everywhere, that you probably never even think about it. Image compression. Specifically, we're diving deep into the JPEG algorithm. You know that moment, right? You snap a photo on your phone, and it just works. It looks great. Doesn't take up tons of space. But behind that simplicity, there's some incredible computational magic happening. We're going to try and unravel how, say, a 46 megabyte image file can shrink all the way down to maybe 4.1 megabytes, and you can barely see any difference.
Yeah, and what's fascinating here isn't just the the mechanic of it, but the why. This whole process, this deep dive, is really going to show how JPEG cleverly exploits the quirks of our own human vision. That's how it makes these huge file size reductions possible while still keeping the resolution and, well, pretty high visual quality.
Okay, let's unpack that then. Why JPEG? Why should why should your listening care about how this old image format works?
Well, connecting it to the bigger picture, JPEG is it's foundational. Simple as that. Almost every digital image from your phone, your camera, probably saved in this format. I saw a recent analysis, something like 86% of images found online were JPEGs. It's basically everywhere. It's silently making our digital world, well, manageable.
So it's really about making files smaller without ideally losing too much noticeable quality. We're talking huge savings in storage, faster loading times.
Exactly. Yeah, precisely. And this ability to compress images so much, it affects, well, everything. How fast web pages load, how much mobile data you chew through. It's huge.
It really is.
Yeah.
But how does it actually compress the image? Is it just like throwing data away randomly, or is there a method to the madness?
Oh, it's definitely not random. JPEG uses what's called lossy compression. So yes, it does discard some information, but it does it strategically. It analyzes little sections of the image and removes elements that your eyes aren't very sensitive to. There's usually a quality setting, right? Like a slider from 100 down to maybe 0. That lets you control the trade-off. Higher compression, smaller file, but potentially more visible loss.
And what happens as you crank that compression up? Does the actual image resolution, the number of pixels, change?
No. And that's key. The resolution, the pixel dimensions stay exactly the same. But if you compress too much, that's when you start seeing those defect squares, people call them. Technically, they're called artifacts.
Ah, the blockiness.
Yeah, exactly. Which raises the really interesting question. How does it know what it can remove without us noticing, at least at reasonable quality levels?
Right, and this is where it gets really interesting, because it relies on the fact that our eyes aren't perfect cameras, are they?
Indeed. It's all about our biology. Our eyes have rods and cones. We have, about 100 million rod cells. They're super sensitive to brightness, luminance, light and dark. But we only have around 6 million cone cells, and those detect color chrominance, red, green, blue. So there's this huge imbalance. Our eyes are way, way more sensitive to brightness changes than to color changes.
So the algorithm literally exploits that imbalance.
Yeah.
That's pretty clever.
Precisely. Think about, say, an image of colorful tulips. If you convert it to black and white, just showing the luminance, it still looks really detailed, right? All the shapes and textures are clear.
Yeah.
But if you looked at only the color information from that same image, just the SIB and CR channels we'll get to, it would look really blurry and indistinct, much less detailed. JPEG totally leverages this. It knows it can sacrifice a lot of color detail without us really noticing, as long as the brightness information is preserved.
Okay, that makes a lot more sense. So, understanding that about our eyes, let's get into the mechanics. What's step one? An image comes in. What does JPEG do first?
Okay, step one is color space conversion. Your camera usually saves images using RGB values, red, green, blue, for every single pixel. JPEG converts these RGB values into 3 new values: Y, CB, and CR. Y is the luminance, that's the brightness component. CB is blue prominence, and CR is red prominence. So it separates brightness from color info. And this step, importantly, is reversible. No data is lost yet. It's just reorganizing.
Okay, so it splits brightness from color. What's next? Is this where the shrinking starts?
This is exactly where the shrinking starts, and it's a big one. The next step is chrominance downsampling. Remember, we're less sensitive to color detail, so JPEG takes the C and CR color images, and it divides them into 2 by 2 blocks of pixels. For each 2 by 2 block, it calculates an average color value, and then it basically discards the individual color values for those 4 pixels and just keeps the one average value. Effectively, the color information gets shrunk to a quarter of its original resolution.
Wow, okay. So the color layers become much smaller, much less detailed, but the brightness layer stays full resolution.
Exactly right. And this step alone removes a huge amount of data. After just these first 2 steps, the image data might be roughly half its original size.
Just like that.
Just like that. And when it rebuilds the image later, it just scales those smaller color images back up. Our brain kind of fills in the gaps.
It's amazing how our brains compensate. You mentioned JPEG also exploits another weakness, something about high-frequency elements. What does that mean?
Yeah, so besides color, our eyes are also less sensitive to very fine, rapidly changing details or textures, what we call high-frequency information. Think about like the texture of fabric or distant leaves on a tree or subtle gradients and shadows. We see the overall shape and contrast well, but the super fine detail, not so much. JPEG exploits this using the next 2 steps: the Discrete Cosine Transform, or DCT, and quantization.
DCT, okay, that sounds mathy.
Mm.
How does that work? Is it complex?
It is pretty complex mathematically, yeah. But think of it like this. Imagine trying to recreate a complex painting using only a limited set of basic brushstrokes or patterns. DCT divides the image, both the full res luminance Y and the downsampled chrominance CBTCR, into 8 by 8 pixel blocks, so 64 pixels per block. Then for each block, it transforms those 64 pixel values into 64 different values called coefficients. Each coefficient represents how much of 64 predefined standard patterns, think like simple gradients, textures, lines at different angles, is needed to perfectly reconstruct that original 8 by 8 block. It's like finding the recipe for that block using standard ingredients. And DCT itself doesn't lose data, it's just a change in representation.
Okay, so it's like breaking down the image block into a set of standard visual components, and then quantization comes in. That's where the real data loss happens for these frequencies.
Yes, exactly. Quantization is the main step where data gets irreversibly thrown away, but again, strategically. We take those 64 DCT coefficients for each block, and we divide each one by a corresponding value from something called a quantization table. Then we round the result to the nearest whole number.
And this table is the key.
It's absolutely key. The values in this table are larger for the coefficients corresponding to those high-frequency patterns. The fine details our eyes don't see well. So when you divide by a larger number and round, what happens?
You're much more likely to get 0, or a very small number.
Precisely. Lots and lots of zeros appear, especially for the high-frequency components. We also use a different, more aggressive quantization table for the CB and CR color components, generating even more zeros there. This step reduces the precision, especially for fine details, but because it targets frequencies our eyes are weak at perceiving, the visible impact is minimized, at least at reasonable quality settings.
Okay, so now we've gone through DCT and quantization. We've got these 8 by 8 blocks represented by coefficients, and a whole lot of them are now zeros. How does that help compress things further?
All those zeros are perfect for the final step, which is actually 2 techniques working together: run length and Huffman encoding. First, the 64 quantized coefficients for each 8 by 8 block are read out in a specific zigzag pattern. This pattern is designed to group the non-zero values together, typically near the start of the sequence, followed by long strings of zeros.
Ah, clever. So you end up with sequences like 15, 93, 06, 0, 0, 0, 0, 0.
Exactly. And then run length encoding, RLE, comes in. Instead of storing all those zeros individually, RLE just stores a count. So that string of 5 zeros might just become a short code saying 50.
That makes perfect sense.
Yep.
Instead of writing 0, 0, 0, 0, you just say 5 zeros. Much shorter.
Much, much shorter. This creates a far more compact representation of each block's data. And then finally, this RLE-coded data is fed into Huffman encoding. Huffman is another classic compression algorithm. It analyzes the frequency of the remaining values and symbols, like the 5 zeros code, and assigns shorter binary codes to the most common ones and longer codes to the less common ones. It squeezes out the last bits of redundancy based on statistical probability.
Wow. That's quite a journey for each little block of pixels. So after all that, encoding, quantization, downsampling, how does my phone or computer put it all back together so quickly when I want to view the image?
It's essentially the whole process run perfectly in reverse. It's quite deterministic. First, it decodes the Huffman data, then expands the run length encoded sequences to get the quantized coefficients back. Then it multiplies those coefficients by the same quantization table values used during compression to get approximate original coefficient values. After that, it applies the inverse DCT, which basically reconstructs the 8x8 pixel blocks from those coefficients. The smaller chrominance, CB, CR blocks, are upscaled back to the original image resolution. And finally, the YCB and CR values for each pixel are converted back into the RGB values your screen can display.
That is just incredible to think about. My phone is doing all those steps: inverse Huffman, inverse RLE, the quantization, inverse DCT, upsampling, color conversion for potentially hundreds of thousands of blocks.
Yeah, like that 4032 by 3024 example image, that's over 190,000 blocks.
And it does it practically instantly. The processing power involved is just staggering when you break it down. So JPEG sounds like this amazing, ubiquitous solution, but nothing's perfect. Are there downsides, situations where it's maybe not the best choice?
That's a really important question. Yes, JPEG has limitations. First, as we touched on, that quality setting directly impacts the quantization tables. Lower quality means bigger numbers in the table, which means more aggressive rounding, more zeros,
And smaller files,
but more visible artifacts. Those blocky patches, maybe some blurriness, especially around sharp edges or in smooth gradients sometimes, push it too far, and the image quality definitely degrades noticeably.
So those blocky effects are basically the result of losing too much precision in those 8x8 blocks.
Yeah.
Particularly for the higher frequency details.
That's a good way to sum it up, yeah. The precision of the whole block representation is reduced, and that reduction hits the high-frequency components harder, making the reconstruction less accurate. Second, while JPEG is brilliant for photographic images with lots of complex textures and smooth transitions, it performs pretty poorly with images that have sharp lines, solid blocks of color, or text. Think logos, diagrams, line art, screenshots with text.
Why is that?
Because the DCT basis functions, those standard patterns it uses aren't great at perfectly representing razor-sharp edges. When it tries to reconstruct those sharp lines after quantization, you often get noticeable fuzziness or weird ringing artifacts right along the edges.
Ah, okay, so for that kind of stuff, you'd want a different format.
Definitely. Formats like PNG or GIF, or vector formats like SVG, are generally much better choices for graphics with sharp lines and flat colors because they use different, often lossless compression methods that preserve those features perfectly.
Makes sense. So one last thing then. If there are newer formats, maybe some that offer even better compression ratios, why is JPEG still so dominant after all these years?
Well, it boils down to a few key things. It's old, it's incredibly well understood by developers and hardware, and maybe most importantly, it's completely royalty-free. There are no patent licensing fees associated with using it. That combination of history, simplicity, relatively speaking, and being free has really cemented its place. Even as formats like WebP or AVIF emerge offering better compression, the sheer inertia and universal support for JPEG keep it dominant. And it's maybe worth a quick mention, too, that the core ideas behind JPEG, like exploiting human vision, transforming data into frequency domains, quantization, many of those same principles are used in video compression, too, like in H.264 or HUVC that YouTube and streaming services use, though video is, of course, way more complex because you're dealing with motion and changes between frames.
What a journey. We've really seen how JPEG compression, by cleverly understanding and exploiting the way our eyes actually work, combined with some pretty sophisticated math, it manages to take these enormous image files and shrink them down dramatically, usually without us even noticing the difference.
It really is a testament to how understanding human perception can drive incredibly efficient technology. These algorithms are often hidden, working behind the scenes, but they profoundly shape our digital experience.
So maybe next time you're scrolling through photos or waiting for a web page to load, just spare a thought for that intricate dance of DCT, quantization, and encoding happening invisibly, all designed around the limits of your own eyesight, making the digital world faster and more accessible.
And it raises a fascinating question, doesn't it? How much of our smooth digital experience is built upon these hidden algorithms quietly catering to our specific human limitations? What other computational shortcuts are happening that we're simply not equipped to perceive?
Definitely something to think about. Thanks for joining us for this deep dive into JPEG. We hope you feel a little more informed and maybe just a bit more amazed by the everyday tech around you.